term work was introduced in 1826 by the French mathematician Gaspard Gustave Coriolis. Simply, work equals the force times the distance. It's usually measured in Newton meters, or joules. In other terms, it's the magnitude of the force applied in the direction of the distance multiplied by the distance traveled. So our first example. You're the captain of a pirate ship and your crew has mutinied against you. They're forcing you to walk your own plank. You've been tied up and set on a 5-meter frictionless plank. If the first mate is pushing you with a force of 10 newtons, what is the work done to send you overboard? So like I said in the previous slide, work is just force times the distance. So in this problem, we're going to have a force of 10 newtons, and a distance of 5 meters. And so then we can calculate simply the work is 10 times 5, 10 newtons times 5 meters, which equals 50 newton meters or 50 joules. So that's work in one dimension. For our purposes, we're now going to show you how to calculate work in more than one dimension.
All right, so now we're going to talk about what happens if we work in more than one dimension. So in this case, we would use vectors and we would perform the dot product between force and distance. So the dot product accounts for the angle between the force and the distance vector, which gives us the magnitude of the force vector applied in the direction of the distance vector, dotted with the distance, which would give us the work. So the dot product is essentially the multiplication of each corresponding component for two vectors. So if the direction of the force applied is not in the same direction as the distance, some of the force will be lost due to the difference in directions. So this will be accounted for in our components of each vector. In this example, we're using 2 dimensions. So as seen in the last example, instead of pushing you off the plank, instead this time the first mate was actually too lazy and he wanted to let gravity do the work for him. He sets up a plank from the origin, which is the edge of the ship in this case, to a point 3,-4 meters away where it plunges into the swirling ocean. Despite your short stature, you actually weigh 100 kilograms, possibly due to an excessive rum belly. The force of gravity equals 0, negative mass times gravity newtons, where g equals 10 meters per second squared. So here we're trying to find what is the work done by gravity to send you into the depths of Davy Jones' locker, like her. So here's our previous drawing, except in this case, the plank is starting from the origin, 0, 0, and it's going down to 3, -4. So our distance vector, in this case, is just going to be this point minus this point, which ends up being 3, -4 meters. And then in the problem, it said that our force vector is actually just the force due to gravity, which is 0, -mg newtons. So if we remember from our last example, work equals force times distance. When using more than one dimension, we use the dot product F dot D. So in this case, we have 2 components for each vector. So we're simply going to multiply each corresponding component, and we get a resulting vector, which is F dot D, which equals our work. So moving down near L'Hôpital, we have work equals F dot D. So here it's going to equal, up here we have 0 times 3, which is 0, plus negative mg times -4. So we're going to get 4 mg. Now recall that in the initial problem we had a mass was equal to 100 kilograms, and then we had g was equal to 10 meters per second squared. So this is going to equal 4 times 100, which gives us 400, times 10 is 4,000 joules.
This production of Dorm Room Professors has been brought to you by Nature Valley. Nature Valley, come enjoy nature with us.